when interacting with the two black holes, what if we are traveling at the boundary at 45-degree line? Can we reach the other side? Like, can we send particles of light if they originate near the boundary at 45-degree line?
Are you talking about?
It's about that two-sided solution.
I go slide.
The eternal Schwarzschild black hole.
Yeah, yeah. So what was the? I didn't get the question. Did you get the question?
I think in the previous Penrose diagram.
Yeah. Oh, sorry. Here. Yeah. So if you send a particle from the right. So in this diagram, people draw these diagrams. They're called Penrose diagrams. They try to represent the causal structure. So where you can go and where you cannot go. So here, light propagates at 45 degrees in this diagram. So if you start here from the right, well, you can stay. Let's say you can follow this trajectory, going basically forwards in time. You can go along this direction, but something you cannot do is move in this direction, right? Faster than the speed of light.
What if we travel along that line?
Yeah, you can travel along here, but you cannot. You will die here at the singularity. You cannot make it to the other side. It looks like you can almost make it, but you cannot exactly make it. So in fact, this is related to. So there are some things you can do, but someone has to help you from the outside to go from this side to this other side. So if you fall in here and then someone collects part of the Hawking radiation and sends it to the person here, they can extract you. So it's a process similar to quantum teleportation, and it's been the subject of recent investigations. But if you just have this geometry and you don't do anything else and you just fall in, there is no way to go to the other side. So it's not a science fiction black hole. It's not a science fiction wormhole.
Hello, I'm just trying to understand a more generalist perspective about the Large Hadron Collider. So I'm just trying to, why is the strong in attracting particles? I am no physicist to probably, I mean, I don't understand the physics part of it. So I'm just trying to understand why is a strongly interacting particle important to understand the black hole, and how does a LHC create or kind of solve the puzzle?
Yeah. Well, I mean, these interactions of quarks and gluons, they are described by the theory of quantum chromodynamics. So they are described by a known theory. It's a theory where it's difficult to do the computations in that regime. And in principle, if you have a big enough computer, or even if you had a quantum computer, you could do the calculations and check the results that you are getting and understand the system. The way we apply the relationship of this conjecture is the following: that we think of those quarks and gluons as giving rise to a five-dimensional space. And in that five-dimensional space, then this new state of matter will look like a black hole. And then we do calculations using Einstein's equations in that higher dimensional space to try to reproduce what would happen. Now, one issue is that for the actual theory of quarks and gluons in nature, we don't know what this five-dimensional spacetime is. So we only know it for a cousin, if you wish, of the theory of chromodynamics. It's called supersymmetric chromodynamics. So it's another slight variation, and it's for that variation of the theory that we can do that calculation. And so if you wish, these black holes are like a toy model where you can. It's not describing the exact system we have in nature, but a similar system where we can actually do the computation. And sometimes you get a better result by changing the theory and doing an exact computation in that changed theory than by doing approximate and wrong computations in the correct theory.
Okay. Yeah. So it creates small black holes, which helps you to understand.
The small black holes in the LHC are something different. So, well, first of all, the LHC has not made small black holes. Okay, at least according to what they've published so far. And those arise if, in certain scenarios of how the whole all of nature works. So they will arise if our particles were confined into some subspace of an extra dimensional space. So there are extra dimensions, that we haven't seen yet. But our own particles live on a three-dimensional subspace, and then there are some other dimensions. And then it could be that when you have a collision, you form a little black hole in this extra-dimensional space. Now, this was a possibility before the LHC was turned on, and the LHC was turned on, and we haven't seen those black holes. But well, maybe you could make them by even higher energy collisions. It requires the existence of very large extra dimensions. So it's, I don't know whether it's likely or not. I think it's unlikely, but it's an interesting possibility.
The de Sitter horizon has a temperature. What accounts for the entropy corresponding to this temperature?
Yeah. So that's a very good question. So I mentioned that Hawking, well, we have this Hawking radiation effect when we have a black hole and we have a horizon. There is another circumstance when we have a horizon, which is when we have an expanding universe. So we have a universe which expands with constant acceleration. We also have a horizon. So there are some regions far away from us that are moving away from us very, very fast, and we cannot receive a signal from those regions. And so for that reason, there is what we call ordinarily a cosmological horizon. In a situation like this, we also have a temperature. So whenever we have a horizon, we'll feel a temperature. And the temperature, again, is proportional to the distance. The wavelength associated to that radiation is proportional to the distance. And this is an effect very similar to Hawking radiation, and is thought to be important in the beginning of the universe to produce the cosmic primordial fluctuations that are seen in the microwave background and so on. So this is an indirect way of seeing an effect that is similar to Hawking's effect. Now the question was more about the entropy. So that horizon also has some area and has some entropy, and so one should be able to give a statistical interpretation also to that entropy in terms of some microscopic degrees of freedom. And we don't have yet a description for that case, because we don't have this boundary far away that we understand well enough where we can see some particles living or giving rise to this entropy. So that's there are many questions that, challenge for some of you here.
There were arguments between Susskind, Tuft, and Stephen Hawking regarding how information is maintained in the black hole.
Yeah.
But you talked about the smaller black holes which die, like they create negative energy and positive energy and die. How does the information is conserved in that situation?
So this whole argument is related to this question of how information comes out of a black hole, whether information is preserved or not. And so the things I was talking about, especially this picture with the particles at the boundary of space-time and so on, is some argument showing that the information is preserved. It does not answer all questions of black holes, because the interior, we still need to understand it. But at least if you believe that this describes the exterior of a black hole, then it's a description where information is manifestly preserved, and it tells you how to compute the information that comes out.
First question is, as you mentioned, if two larger black holes collide, the ripples are created. And what are the after effects of those ripples created? Does it affect the space-time, and does it affect the celestial bodies all across the solar system and galaxy? And if so, how do you measure the after effects of those ripples created, and that affects the celestial bodies? Yeah.
So, well, if the two black holes collide and you are close to the collision, you will have these gravity waves that they will shake you, right? And if you are very close, they will take your head and your feet apart and destroy you, right? But fortunately, there are no black holes that are close enough for that to happen. And these black holes that have been detected collided, more than million light years, 100 millions of light years away, right? And so they are so fast that their effects here are very, very tiny. You need the super sophisticated, very sophisticated detectors to detect their influence. They have an influence. It's very, very small. And of course, we don't feel it in ordinary life. But with these very sophisticated detectors, you can detect these very tiny effects. And that's how they detected this black hole collisions.
Thank you. My second question is, if an object is there, it just goes into the black hole, and you don't know what happens with that object, but the properties and the light of that object still stays there. So is it possible for us to retrieve the light properties of that object from the past?
Yeah. So if some object falls into the black hole, the light that is emitted is going to look it's redshifted. So it means that so you send an object which looks let's say white, and it looks redder and redder, and the radiation from that object will have lower and lower frequencies until the frequencies will be comparable to that of Hawking radiation. And then it will be swamped by Hawking radiation, and you effectively won't see it anymore.
Okay, so it's not almost possible to retrieve the information?
No, no. I mean, in a time of order...
like sequence of incidents in...
no, I mean, let's say a black hole has some size, right? But more or less a time that is proportional to the time it takes light to cross that size, the object will have disappeared. I mean, a time of that order times some logarithm, so it will, the object will have effectively disappeared.
You said that a smaller sized black hole has a higher temperature than a bigger black hole.
Yes.
So if I have a large sized black hole and it is radiating away and getting smaller, so how do you explain by this mechanism that the temperature increases for a black hole that is radiating away?
Well, the black hole is radiating and it gets smaller, right? And then the temperature increases. So the fact that, okay. So you say the energy, so you are having in mind that an object energy decreases should have a decrease in temperature, right? And that's true for most physical systems, which have so-called positive specific heat. But the black holes are weird systems that have negative specific heat. Their energy decreases and the temperature increases. So if you were to put a black hole in thermal equilibrium with a gas, it would be an unstable situation. Either the black hole would start growing or it would start shrinking. But a black hole could not be in equilibrium with a gas at fixed temperature because it has its negative specific heat.
How do matter behave under gravity wave? Like you told that if we are near the black hole, we'll be head and body will be up.
Yeah.
So is it just an illusion, or like if we are having a solid metal block? If we have a metal block, so I'm worried about the physical property of it being a mechanical engineer. That it will be kind
so
of tensile strength for a material.
Well, if you have a metal block, the block will be stretched.
Is it an illusion or really it is getting stretched?
No, it's getting stretched. But I mean, in fact, that was one strategy that was followed initially to detect gravity waves. They made, Weber, I think was the name of the person. He made metal bars, and he was trying to see that when gravity waves would go through it, the bar would start oscillating. But that was a coarse method. The gravity waves that are naturally produced in the universe are not strong enough to do that, to show something detectable. And so the actual way in which it's done, it's through an interferometer. So you have a central mirror, right? And then two other mirrors and light traveling between the two, and you detect how the whole contraption shrinks. So, but the principle is the same. So.
Thank you very much. So thank you very much for joining us today.